Okay, ladies and gentlemen, you have seen several explanations in the previous two lectures on how we can explain observations in the sky based on the heliocentric model, the model where the sun is in the middle, the earth goes around the sun, the moon goes around the earth, etc. I also mentioned that in each of those models we could work things out with the earth being in the middle. What I'll do in this lecture is I will show first of all how history led us to this situation where we could explain everything with the earth being in the middle. What led us to that? And then I'm going to show you one specific explanation that led Copernicus to his revolution. Therefore, this story is a story of the revolution, the in capital T. We do not know for sure who was the first person or the first culture even to merge logics and astronomical observations. It was most likely the Egyptians or the Babylonians, but it could have been the Chinese, maybe Native Americans, maybe Africans. Most records from these eras are lost. Still, have you seen the Indiana Jones films or the Lara Croft mummy films? Did you ever wonder if they were right about what happens when the sun or moon strikes certain objects? I'm not sure about waking up a 4,000-year-old mummy, but I know astronomy was religiously, pun intended, followed. It was followed in agriculture, in architecture, and in religion. I know some crazy myths were associated with the unusual motion of some stars relative to almost constant constellation. You've heard of such religions. They're called astrology. Now that is very different from astronomy, which is the field of observing the sky without interpreting it. We do have many records of Greco-Roman astronomy. What we do know is that by the end of the Roman Empire, precise observations without telescopes resulted in increasingly refined models, however wrong, that explain stuff. Phases of the moon, eclipses, the seasons, they were all explained by those fancy models that in principle had the Earth in the middle and everything revolving around us. Things got way worse when Europe fell into the Dark Ages and went back to believing the Earth was flat. In that time, the Muslim world kept the Greco-Roman knowledge alive and added recent innovations from India. Ibn Qura, Avicenna, Al-Ghazan, and others kept refining those models and invented new stuff. Think algebra, algorithms, inertia, and optics. By the late Middle Ages, Europeans such as Roger Bacon and William of Ockham and others learned of the Arab inventions and used these in challenging Greek ideas at the time of the early Renaissance. You may have heard that simpler models are more likely to correspond to reality. That's actually a William of Ockham accomplishment. You may think it's common sense, but it's not really. In a world where might was right until that time, ideas, however convoluted, were considered the winners because the winner was the guy with the most force. So it was a revolution. The simpler the explanation, the better it is. It's known as Occam razor or the principle of parsimony. As promised, here's an explanation where the sun is in the middle, which would lead a fellow by the name of Nikolai Copernicus to the idea that the sun must be in the middle. Think about Venus going around the sun. For one thing, Venus is always close to the sun. You'll never see Venus at midnight. If you do, it must be really, really inebriating. Venus is never more than 3 hours after sunset or seen 3 hours before sunrise. These are the maximum western elongation, that's before sunrise, and maximum eastern elongation after sunset. If you're not sure how that comes about, put that big clock in the sky around the Earth on a picture attached to this slide and try and work it out. Just draw, please do. Alright, that was a hello from my cat. But what I want to say next is this model is going to lead Copernicus into seeing the following. When the part of Venus that's illuminated is very far, Venus is very dim. That makes sense. But when Venus is very close to Earth, it should in principle be illuminated in such a way that we would see a little brighter light. And what happens is that it's not exactly as it should be.
So here is the crux of the matter. Look at what's happening if Venus is going around the Sun rather than around the Earth. If you had a telescope, you would see this exact picture. Notice what's happening starting with the tiny Venus by the other side of the Sun. It then turns into a gibbous Venus, still fairly small, then half Venus, still fairly small, then a crescent Venus that's fairly large, then a tiny, very, very little illuminated crescent Venus that's right next to us. So it's growing, getting a little dimmer, then brighter again, and then dimming. Copernicus cataloged the brightness of Venus without a telescope because he did not have one. The telescope was not yet invented. Yet he cataloged those brightnesses of Venus, and in the introduction to his book emphasized that this was the reason that he believed that the Earth is going around the Sun and Venus is going around the Sun rather than everything going around the Earth. More on that in the next lecture. Then came the revolution after which all revolutions since are named. When Copernicus came along, he knew his models must be simple enough, but still he knew they need to explain precise observations. His models actually still assumed that the planets orbiting the Sun are moving on perfect spheres and moving on epicycles. It is quite clear, though, where the word revolution comes from. It comes from the name of his book, On the Revolution of the Heavenly Spheres. This slide is just the simplest model of Copernicus, and it is here in order to explain to you or remind to you the order of the planets from the Sun outwards. The Sun, Mercury, Venus, Earth, Mars, and not included in the picture are Jupiter and Saturn. Other planets were not known at the time of Copernicus or Kepler. Note that the symbols in this image are the same symbols we're using to the present day. For example, Venus and Mars may be quite familiar to you guys. Here is his first known improvement. As we have seen, this model shows that Venus is the evening star and then the morning star. The actual brightness graph is on the next slide. Please note that this morning star evening star exchange is also true for Mercury. Mercury is even closer to the Sun. This graph corresponds to the previous slide. Magnitude is the most important part of this graph. Notice how the brighter it is, the smaller the magnitude. Interestingly, this measurement was invented by Hipparchus at about 200 BC, so a long time before Copernicus. It is kind of backwards. The smaller the number, or the more negative, the brighter the object.
It's even weirder that to this day astronomers use this device for measurement of brightness. Retrograde motion is the greatest triumph of the heliocentric model, the revolution of Copernicus. As was explained in previous lecture, the retrograde motion is the motion of the planets relative to other constellations, for example Orion. A planet would appear to move east-east-east, then change its motion towards the west. Of course, this is over the course of many nights, and then move east again. This retrograde motion happens roughly once a year for most outer planets, maybe a little less or a little more. Here we see, for example, that if you would just see that Earth's orbit, where the numbers grow a little bit more rapidly, meaning the planet is moving a little faster, when you just look at the lining up of that with Mars in the outer orbit, you get that east-east-east, then west, then east motion. Read this question and try and get the answer. I usually, with those multiple choice questions, give roughly 20 to 30 seconds. Okay, the correct answer here is B. As you can see, and according to the previous picture, when the two orbits, for example, Earth and Mars, are slightly off, the retrograde motion does not occur on the same line. It depends on how the tilt is happening. You may get this backwards motion or retrograde motion to be in the shape of Z, or a loop that's not quite symmetrical.